Very, very happy to be here. First time in Paris. It's very nice and such a great program that's put together. I really enjoyed yesterday. So hopefully today is my jet lag is a bit better. Hopefully, so I'll deliver this well. So yeah, thanks for the introduction, Adrian. Again. I'm an assistant professor at UC Berkeley, Electrical Engineering and Computer Sciences, and also adjunct in UCSF. So I do not have a medical background, but my work is in the intersection of AI and neuroscience and neural engineering applied to spoken language. So okay, so this is the very familiar, uniquely human speech communication chain. What's happening right now is, I have all these thoughts in my head that I want to impress upon you. My thinking about how neuroprostheses must be done, and instantaneously, all those thoughts are taking form of the lexical sequence of words that I want to say. And I am orchestrating these muscle movements in my mouth so that the air transmits the message that I intend to convey. And you have the reverse process of decoding my message, right? So that's the auditory pathway. So my work in today's talk, I'll basically talk about this forward model of forward path of how brain orchestrates these orofacial musculatures to convey sound, speech. And I'll talk more about the historical timeline of how this came about and what has happened in the last decade. And it's more of a first-person narrative of how to think about speech neuroprosthesis from my view. So it is focused on my works, but it kind of is correlated very well with how the field has also moved, so that's nice. What's unique about spoken language that I like is of all the transformations that happen, it starts at the cognitive signal, a linguistic signal, a muscular signal, a motor signal, an acoustic signal. So whatever the background you have, linguistics, signal processing, machine learning, AI, or cognitive science, you can study spoken language. And that's what's excellent about it. And it's the problem and opportunity, though, is we don't have a model system. We don't have any other species that has such a developed spoken language system to convey information. So that's a unique opportunity that we have. And it's not now that we are looking into this. It's over 100 years ago that Harry Cushing has kind of stimulated these parts of the brain and evoked sensation or stimulation or movement in these parts of the brain. As you see, there is like a structure of where the lips and the jaw and the tongue are. So this is 1906, right? And of course, this was developed by Bouldre and Penfield into what's the motor homunculus. You can see very well the amount of cortex that's dedicated to the most important functions. We are very dexterous animals, so the hands, of course, have a very big representation, and so does the orofacial musculature. So you have your mouth, your tongue, all of this here. Whereas we have a very good understanding, and thanks to Dr. Anderson's talk yesterday, about how arm movement and hand movement can be represented and decoded. Spoken language has lagged very much with respect to that, notwithstanding the amount of cortex that's dedicated to it. And that's largely because behavior is hard. Whereas in hand and arm, you have a center of task. You have one target, you go and come. Whereas while I'm talking now, it's rapid stream of motor commands that are happening. Right now I'm speaking like 120 words per minute, so that's really a lot of spatial, spectral, and temporal precision that I'm controlling. That makes it hard. And but we have made some strides, of course. So here is okay. So this is very zoomed out, but this is from a review that just got published from the Eddie Chang's lab, and it's kind of a timeline starting from the early works. Early electrophysiology really tried to do can we decode 5 vowels or 5 consonants, and can we decode the formants of sound. And more recently, I think the takeaway from this slide, if it's too small, is that there is this recent burst of activity and interest in decoding spoken language signals from the brain. And also included, of course, is what Professor Anderson talked about yesterday, Sarah's work on imagined speech. But so I'll talk about some of the works that I've been personally involved in, kind of the updated versions of those talks, but also something that is really unpublished yet, but very, very new. What has happened that's remarkable now is we have all these different modalities with which to probe the brain at different resolutions, either space or time. So you can go all the way from single neuron activity using microelectrodes, or full brain with fMRI, MEG, and all these other modalities. But there is always a trade-off, right? You have either a good time resolution, or spatial resolution, or spectral resolution. But for something like spoken language, which is so rapid and fast, we really have to be invasive. All of my work is restricted to this one modality of ECOG, which is this is kind of the putative ECOG grid, if you will. That is. It's been introduced yesterday, I believe. So for people, and to this crowd anyway, it's not new, but it's this array of sensors that are placed right on the surface of the cortex. So nothing's going in; it's just sitting and listening to the voltage. And this is a reconstruction of where it would be put. Kind of what's nice about ECOG is both the time and the space resolution that we would like to probe the structures that are involved in speech production. Here is an example of what one electrode, for example, encodes. So this is, I believe, a perception task. So the participant is listening to a sound, sir. And this is the time-locked average response to all the trials of listening to it. And here is a single trial response. So you can see very high SNR, which is great, enables us to study all these things. And it's kind of driven a lot of understanding of the functional organization of different auditory structures initially, but then we also had some motor insights that followed right after. So the questions that we could ask are, of course, now I'm interested in spoken language. I want to understand what, and more on the production side. Auditory perception is relatively more well studied, but production less so. But that's where I came from, with an interest in understanding how we produce speech sound, and can we decode the entire brain to kind of synthesize what the brain is trying to say. So the first, about 10 years ago, there was this study, which is kind of a rehash of Bowlby and Penfield's stimulation work, but not with stimulation, but with just recording, right? We are just sitting on the cortex, the ventral sensory motor cortex, and listening to what's happening with respect to the voltages as participants were saying simple syllables like ba, poo, ga, and so on, right? So, and what you see here is the time rasters of what's happening in different regions. And with simple linear analysis, we can figure out that there is this map of the vocal tract in the brain with respect to like where each articulator exists. And of course, there is two regions for larynx, which is very uniquely human. Other NHPs do not have that, two locations. Anyway, so that was interesting, and that really got me interested in, okay, so this is great that we have a map now. Can we go to fluent speech? Because fluent speech is not merely stringing together discrete chunks, but it's really amalgamation both in time and how these syllables are orchestrated. So, so that's what I wanted to understand is like, what are the mechanisms of fluent speech production, like the one I'm doing right now? So we started a new task where subjects who were in treatment for epilepsy were implanted with this grid of electrodes, and if it's in the sensory motor cortex, the region that's assumed to control speech articulation, we kind of ask them if they would cooperate for the study, and usually they do, so that's really nice of them. So they read sentences like this, and we simultaneously record neural activity and the sound that they produce, and extract the high gamma feature that I've shown in the last slide. And of course, what we would like is to relate the neural activity with behavior. Now, the behavior during speech production is really movement of the mouth, the lips, the tongue, and the jaw, right? So we kind of take a step back and as a behavior. Now, behavior cannot be simultaneously recorded with the brain because it's its own thing. What you see here is the setup for mid-sagittal articulography, or like sensors placed on different parts of the vocal tract, and the subject speaks within a magnetic field, so we can track the movement of different regions. And so here is example trajectory of the upper lip, lower lip, tongue tip, and so on. You can also do MRI. There is real-time MRI data sets that are available now. We kind of use EMMA for its ease and sufficiency. A big part of my lab is dedicated to understanding how well we can estimate vocal tract behavior just from the acoustic signal and vice versa. Like if you had kinematics, can we synthesize speech sound? So I'll play two sounds. The first one is the original sound. We then estimate the vocal tract behavior. So these are just displacements of all of these sensors in the X and the Y direction. What you can see already is what's in dashed lines are the ground truth. Someone was actually recorded in a scanner while they're speaking, and what's in solid lines is the actual predictions from our algorithms. And you can see there is a very good correlation of these 12 features, but what we are doing then is synthesizing speech from these representations alone. So, I'll play a signal.
He was attached to the Texas Militia Air Force.
So it's a very English sound. I'll now synthesize that sound from this articulatory substrate of the representation.
He was attached to the Texas Militia Air Force.
So it was perceivably not at all different, right? So what it really tells us is we can go into the physiological substrate of the speech representation in a way that preserves the intelligibility upon synthesis. So we have machine learning algorithms that we are working on that efficiently do this. And this is kind of now getting to be a solved problem. We can do this for people who are not even under the scanner, but estimating what behavior they would have gone through. Now that, going back to the encoding study, now that we have behavior that's well aligned to the acoustics, we can now ask simple encoding questions. It's like, what exactly is happening in this cortical location to enable this pattern of motor activity to happen, right? So we take this window of behavior, we encode with simple linear model what exactly should be the weight, the mixing matrix for us to predict what's happening in this electrode, right? So you can see that we can very well predict, but if you look back at the weights and plot them back on the vocal tract, we can understand what exactly is happening for this electrode to move the weights moving. So what you see here is the weights plotted on the vocal tract. So this is a space-time motif, if you will, a pattern that is invoked in a single cortical location, right? In fact, if you go back to the sentence, it was some stimulating discussions, and this is an electrode that does the tongue tip, right? So when you say s or t or na, like that's the tongue tip going and touching the palate, right? So that's kind of the trajectory of that electrode, if you will, or that is the tuning of that electrode. So indeed, so this is an electrode that's a little north of what we just saw, and it's responsible for a labial movement pattern. So what you see here is lips coming and touching each other and going back. Right? So this is a labial pattern of all the lip movements. And likewise, here is okay, there is another that's just the dad. So we have across 5 participants that undertook this experiment, we had 108 cortical locations, and we had this very nice clustering of 4 distinct regions of patterns of electrode activities, right? So we had movements of the tongue tip, movements of the back of the tongue, movements of the lips, movements of the larynx, meaning for the pitch control or voicing and so on. But what's remarkable is there is a shared gestural space. So these are like the code book, if you will, of speaking. Like how the phonetics are the kind of the code book of listening. These are the motor equivalents of speaking. So that's what we found that was really interesting. And that really pushed us to ask, now can we use this to decode the brain? Can we decode these signals? We have done this encoding study to understand what's happening in the brain, but now can we use all of the engineering that we have to decode all of the cortical activity? So indeed, this is what we've done in a 2019 study where we had a very biomimetic design, if you will. So we were recording all of these electrodes from the brain, and we were regressing using recurrent neural networks and LSTMs at the time. So we would then predict the kinematics or the movement parameters of different parts of the vocal tract, and we then would synthesize those into speech. So that was our model of kind of showing a first demonstration of can we decode intelligible speech just from neural activity. And indeed, that's what we've done. What you see here is the, so these are people who have epilepsy, they can speak otherwise, right? So we have ground truth. Like these were the sentences they said, and using the algorithm we've just developed, we have gotten this reconstruction, which if you kind of can see, the spectrograms are very well correlated with each other, and kind of it was very compelling for us to like listen to what exactly it sounds like. So that's what we did. So I'll play the first sound without biasing you, just what's reconstructed from the brain. So that's decoded directly from the brain. So cortical activity turned into movement, turned into sound, right? And this is the original.
Shipbuilding is a most fascinating process.
So I do not know if this plays again, but yeah. So I'll play that again just to, or not. It's probably just moved on. Okay. Anyway, so that I hope was convincing enough that we can reasonably reconstruct neural activity to intelligible or semi-intelligible speech signals, which was interesting. But the real North Star for our project was to understand if we can do this for someone who is paralyzed, who has lost their voice function due to either injury or progressive neurological disease like ALS or motor neuron disease, and can we reconstruct speech back for them, right? And so we had, in 2019, we started a clinical trial at UCSF called BRAVO, which stands for BCI Restoration of Arm and Voice. If you remember the homunculus, the hand region and the orofacial are really next to each other. So the hope is with a single grid of ECOG, we can get both of them. That's the idea. I do not personally work on the arm, but we have collaborators at UCSF who do. Kind of what we wanted to tackle was, so at the time we were doing, of course, arm decoding was very well developed. We had robotic arms back in, 2006. What people were doing for assistive communication was still using technologies like screen readers or gaze tracking on a speller on board on a monitor, and then they would select each letter at a time. And these are participants in our study. This is Pancho, who actually the way he uses this is he has a baseball cap with a stick on it, and then he pecks on his monitor to select his letters. So it's, and he's a web developer. Remarkably, he can use this very primitive infrastructure to actually design things, drag and drop things, and so on. And this is Anne, who, so both of them have lost their function, one to stroke and one to an accident over 18 years ago, both of them. But their current assistive communication is really suboptimal. Here is kind of a scale of communication rates, if you will. So number of words per minute. Whereas I'm talking anywhere between 120 and 150 words per minute, the current BCI interfaces are really, really slow. Like we have less than 10 words per minute. And BCI-driven cursor control at the time, out of the BrainGate clinical trial, was adapted to move a cursor on a screen to select the letters. That was kind of the communication state of the art, but it was really tapping into the movement substrates, not the orofacial substrates of the brain. But given what we've seen with our decoding efforts, we figured we could try and build direct speech decoding BCI, tapping into the spoken language structures. So anyway, that's what our goal was. And so that's, Poncho was the first participant we implanted, and kind of proof of principle that we can do this. So this is the grid placed on the sensory motor cortex. And the first study we did was a very simple 50-word closed vocabulary study. So these were still in a classification setting. So we had one of 50 words that were getting detected. And this was the error rate that we were getting, and a speaking rate of 15 words per minute, which was comparable to his existing packing mechanism if we had predictive typing there as well. But essentially, we kind of used all the tricks that were in the literature for something like your Apple Siri or Google Voice, kind of using language models to correct the outputs of our BCI and so on. So we could get decent performance on this limited vocabulary task. And this was 2021, which was not so long ago, but the field has moved so much more beyond that point now. So that's that. And so this is, in 2022, we have kind of extended that algorithm to kind of a speller interface. So the participant would say things like Alpha, Bravo, Charlie, like the NATO code words for the entire alphabet. So we kind of made him use the interface by saying things like Alpha, Victor, Alpha, Lima, and so on. So this is kind of, okay, so this is, so as you can see, that's his interface. That's the pedestal. It's a USB-C that's kind of plugged into my MacBook right now. One of those things, and very similar to the UTARE and the pedestals that BlackRock built for them. But kind of what's happening here is we are decoding one of 27 classes, and we have predictive language models that kind of combine them together, very much in the light of how speech recognition acoustically happens, and those are combined. So this is a speller interface. Of course, this is much different than what we've been hoping to do. I started with describing speech as this naturalistic modality, which has this high information transfer rate, right? So we were trying to explore how we can do this with speech directly, and not a classification paradigm as I'm showing here. So indeed, in our latest participant, Anne, we implanted a grid, again in the ventral S1 and M1. In all of our studies, there is no such clear distinction between the sensory and the motor substrates. It's spread out, but maybe it's the ECOG there. But that's where our grid is implanted, and we kind of recreated all of the works that we have shown in Poncho, the earlier participant. But what we have done, and this was published last year, was this trimodal decoding architecture. So we had we had to decode three things. One, we wanted to create an interface that could decode the text of how they're speaking and the speech, and also we had another modality I'll talk about. But this is our architecture for text decoding. So we have neural activity coming in, and we have a bidirectional recurrent neural network, and it would kind of estimate these phoneme probabilities of how close it is to one of the phonemes of the language, and these would then be used within a search algorithm called CTC, which is kind of used in your Google speech recognition, for example, to kind of estimate what was the best sequence of words that corresponds to this cortical activity. So that is what this interface was, and we kind of went to 1,000+ word vocabulary. I think it was 1,100 some number, and the communication rate then was 78 words per minute. So, and it was not restricted to a very definite closed vocabulary. They could say any combination of these words within these 1,000 words, which is getting to the point of being useful. And again, that was directly to text. And of course, I'm interested in the direct speech decoding approach as well. So we had speech synthesis also coming from this. So in parallel to all the developments that were happening in the neural engineering fields, AI has exploded. We now have very good pre-trained models of speech and language that we were having access to. And we kind of do a whole lot of probing analyses on some of the big pre-trained models that are out there. And one of the models for speech is what's called Hubert, which is trained using self-supervised learning, which kind of, the way it works is you have a speech signal, the waveform, if you will. If you had to like quantize that into like different codes, and if you ran self-supervised learning, meaning you mask certain codes and then predict it from the context. So this is kind of the architecture that's powering the ChatGPTs of today, but they're doing it at scale, of course. But this is what self-supervised learning does. But what it does is it kind of gives us this very predictable sequence of codes that describe acoustics. So that is what our target was. So we had this sequence-to-sequence model that would take in neural data and predict the sequence of codes, discrete codes that can then be used in a unit-to-speech vocoder. We could design custom vocoders that would go from these discrete units into speech, like you see there. We also did something, so Anne, this is Anne's voice from her wedding video. It was a very grainy video with a lot of muffled voice, but we kind of cloned the voice characteristic from that video and imposed it on the BCI algorithm, and that's what we did. And this is where you can see that we were, for 1,024 word vocabulary, we were about like 50% word error rate. Word error rate is this number, like how many words are wrong or wrongly decoded by an ASR system or a listener. I believe this is all using Whisper, speech to text algorithm, and we are decoding that. So that's one modality. So the final modality is, of course, I'm not just communicating using speech using the computer. I'm using my face. I'm gesturing with my face. I'm showing emotion. And likewise, in communication, facial expression is a very important trait. Kind of, we are very multimodal creatures, both in production and perception. So we kind of used this company, Speech Graphics, which kind of does this for video gaming and kind of facial rendering. But we kind of used their platform to also create discrete gestural codes of face movements. And we had our participant do different gestures like tongue raising, lip opening, lip rounding, and so on. And we were also decoding those features from the brain. And also emotion. Right, so this is, for example, a classification of different expressions. So lips, mouth closing, mouth opening, lowering the tongue, raising the tongue. And you can see a very clean diagonal matrix in terms of confusion. So the signal is very clean, and her expression, so we are not really decoding emotion, but we are decoding the facial or the articulatory substrate of emotion in how we express it using our face. And that's what we're decoding. And of course, we did ask her to emote these expressions, and we could classify very well how that looks like. So, so this is a kind of a summary video that should kind of give you the entire setup. So I let it play out, and you'll see some examples of 3 modalities being decoded from her brain. So the setup is she's trying to speak a sentence. When there is a go cue that turns green, and then we're decoding all 3 modalities. So that's the target sentence she's trying to say, and the go cue is turning green. then you can measure how
You are wonderful.
right. So that's her trying to say that sentence. There's another, I believe, a couple more.
Give me a few minutes. What do you think of my artificial voice?
Right. So that's actually her voice from pre-injury that we recreated. But let it play out.
What have you been doing?
Okay. So as you can see, there is a very long delay between the go cue and the attempt and the sound coming out or the face moving. And kind of this latency bottleneck is coming from the task design itself. We have the sequence-to-sequence model. So she has this entire sentence she's trying to say, what do you think of my artificial voice? And she takes her sweet time, and then it kind of sends it to the decoder, which is, so this was published in Nature with that latency. We were happy about it, but of course that was not very convincing because this is not natural, right? This is not how I'm speaking right now. It's almost instantaneous how my intent to move is kind of executing in real time. So this part of what I'm showing now is kind of unpublished, but brand new. So what we have been working on lately is streaming approaches. These are more naturalistic, so we are not waiting on a sequence-to-sequence style architectures, but we are doing more streaming architecture. So we kind of have this buffer of neural activity that we are kind of running through the brain data, and as and when we have enough confidence that we have enough evidence to add things together, we are sending it off to the decoder to convert into these tokens that are then merged into speech. So this is a very seamless architecture, but it's a lot of engineering in terms of kind of adding bits and pieces of speech to make real sound in near real time, or as best as we could. So, what's nice about this architecture is that it's very naturalistic. It has the potential to be closed loop, whereas current brain-to-speech architectures do not. It is approaching closed loop. I'll say it's approaching because closed loop is kind of ill-defined in the situation of someone who is actually impaired. Like, we do not have the ground truth of their attempt. So it's kind of ill-posed to begin with to measure the latency. But we do it. I'll describe how. But we also use this architecture. It's called an RNN transducer, which is kind of another thing that the speech engineering world has been developing for very low latency speech recognition. What you see here is free-form decoding of an entire block of 6 minutes. Right? It's an entire 6-minute block of our participant attempting to say things. What you can see clearly is, again, the task structure is similar. There is sentences that are going on, and then there is go cue, and then she's beginning to say things. So, this black dashed line is the actual go cue that's happening, and the blue is the detected speech onset from her brain alone, right? And the decoder has the intent to move kind of implicit in it, so that it can run through the entire block and only generate speech where her attempt is. As you can see, there is very little lag between the go cue and the detected attempt and the speech coming out, right? So this is all generated speech in the waveform. So we are approaching what I would call is near real time. But we have a much better communication rate for brain to speech, and it's also generalizable. We have run the same architecture on ECOG, of course, that's this study. We did this also on microelectrode arrays. This is data from the BrainGate group that has concurrently worked on the brain-to-text algorithms, but there was no brain-to-speech in that situation. So we kind of employed the same algorithm on that data, and it's comparable. If someone's curious about would you go ECOG or microelectrode, well, it's comparable. It's really a matter of we cannot answer this question unless we have the same participant implanted with both, and that's not going to happen. But another case that I want to show is EMG. So this data set is facial EMG, where a healthy speaker is placed with EMG sensors, and they're speaking, and we are decoding essentially the same architecture on that data. Right, it's comparable. What's very reassuring for me is that the EMG data, meaning the speech generated from EMG signal, is comparable in terms of word error rates to the ECOG in the MEA. Of course, it's a little better in the delayed CTC case, but the streaming architectures are in fact comparable. What this means is we are doing the best we can with respect to converting the brain signal into sound. And we are doing as well as we would if we were measuring actual healthy muscle movement, right? So that's something that's reassuring. We are kind of squeezing as much juice as we can from the brain data. Those are the kind of the highlights of this, and I'll end with a demonstration of how this streaming architecture works. So look at the latency, which I think would be more appreciated now given what you've seen before. So it's speech that's streaming in near real time. We are not waiting for the sentence to be completed. So there's a couple more. So I did not really cherry pick anything. This is an entire 5 or 6 sentence sequence, and I think there is also some errors in there.
Is that they I and you?
I think this is the last one, I think. Let's see.
What would you say? Hey?
Okay, this is the last sentence.
I know that, but you can now.
Right, so that's the end of that demo. So it's what I would call is more naturalistic. It's not really natural, but it's approaching latencies that are more acceptable and getting to a more acceptable communication rate. And kind of what we want to evaluate now and where we are right now is kind of studying the closed loop behavior. Can the subject now control aspects of the volume of what they're saying, the jaw opening, the pitch, and so on? These are all what are now possible given this architecture that would not be otherwise. Anyway, so that's the end of that. So it's kind of, the preprint will be out anytime soon, and check out for that. So what I believe is the future is, we are, of course, there's commercial interest also in this, and with or without our help, there will be wireless, low footprint, high density interfaces to measure brain signals. What we really need is more grounded models of spoken language. When I say grounded in the cognitive, motor, physiological underpinnings that underlie spoken language even in healthy participants. What's remarkable is these structures still exist decades after their impairment, which also resonates with what Professor Anderson said yesterday. So that's nice to see, but what we have to really do is close the loop with more interesting designs that are grounded in the science so that it's intuitive to embody the subject, and then they can learn in the closed loop. That is kind of my thoughts, and more interdisciplinary research is what's really needed to push the field forward. But I think this is a great time to be in this field. So for the students who are trying to get in, this is the right time. All right, so I'll wrap with all the acknowledgements. So my group is here, but we also had a lot of collaborators from Eddie Chang's lab at UCSF in this work that I talked about. But yeah, thank you.